Good evening, everyone. We're about to get started. I'm going to add Matti to the stream. Hi, Matti. Good to see you.
Hi.
How are you doing tonight?
Good. I've got my cup of tea all ready for interesting evening of discussion.
Yep, that's the plan. So wait, let me add the... Maybe we can chat before I start sharing for like a minute. So the plan for tonight is that Matti and I want to like have a chat about a project that we've been working on sort of more active recently. I started working on it this summer, and Matti joined me in fall. And in the last couple of weeks, we've both been rather active on it, and we wanted to like do a bit of a technical deep dive into it tonight. And this project is called Pydrofoil, and it's a RISC-V emulator, a fast RISC-V emulator that's reusing a lot of the PyPy infrastructure, like the PyPy JIT, the PyPy garbage collector in some places, and like also the PyPy static optimizer and the PyPyC generator and stuff like that. Right. So
when you say emulator, what does it emulate? Like what? Right. Where does this all start?
Yeah. Okay. So let's actually start at the very beginning. So I'm not really a hardware kind of person. I only do like dynamic languages usually. But this summer, a friend of mine like asked me whether I like didn't want to try and do a hardware project, and he's involved with a CPU manufacturer, and he told me that like in the CPU space, there's this language called Sail, and Sail is a domain-specific language. Here's the GitHub of that. Sail is a domain-specific language that's used to very precisely, in a very precise and abstract way, specify how a concrete CPU is behaving. Right. So it's a DSL that you can use to explain in a very high-level manner what exactly happens if you say execute an ARM instruction, right? And if you want to do this specification, then you would have to write a Sail model for your instruction set architecture, ISA. In this case, ARM. But like the Sail model that we're concretely going to talk about tonight is another Sail model. And that's basically a Sail model is a program in this domain-specific language, and the domains, like the program that we're going to talk tonight about, is the RISC-V model written in Sail, and that's basically a specification of how the RISC-V instructions actually what they do, like what it means to run a specific bit pattern on a RISC-V machine. Right.
So when you say it's a DSL, or is it actually a program written in that DSL?
Right. So Sail is the name of the programming language of the DSL, and the purpose of Sail is that it's meant for writing descriptions of how a CPU behaves in this Sail language. And one of the descriptions one of the programs that we'll talk about now is the RISC-V implementation in this language, right?
And what's the relation between, say, Sail and something like HDL, if you know it, or another?
Right. Yeah, that makes sense. So Sail, the purpose of, the motivation for the Sail project is really precisely reasoning about the behavior of an instruction. It's not really talking at all about how you would concretely implement this instruction, like in hardware, in concrete transistors, right? So it's really the purpose of this model is to reason about the correctness of your hardware implementation or the correctness of your compiler. For example, if you want to do a correctness proof for a compiler, you need to prove that the C program behaves correctly with respect to the C semantics. And if you compile it to RISC-V assembly, you want to prove that the that the C behavior and the behavior of the resulting RISC-V program is identical. And the problem is, in order to do that, you need to know what the RISC-V instructions actually do, right? And so that's where the sane model comes in. So the sane model is a description of the precise behavior of the RISC-V instructions that you can use, for example, to concretely do proofs of correctness of compilers, or you can also use it for proofs in the other direction. You can try to use it to prove, or at least exhaustively test, that your hardware implementation that you're writing in something like HDL or Verilog or something, that this behaves equivalently to the spec, and the spec is expressed in this say language.
So you can use this to actually confirm and to prove that your implementation satisfies a spec.
Right. I mean, I don't really know how this part works, right? So okay. I don't know whether there are concrete approaches to sort of really prove the equivalence of implementation and spec, but it's definitely a very useful testing tool, because you have the say RISC-V model is the golden model. So it's really supposed to be the ground truth for how RISC-V is supposed to behave. And that means if you have a difference in behavior in the hardware, in a concrete hardware implementation, then, I mean, you might also find a bug in the spec, right? I mean, the specs do have bugs, but sort of the baseline assumption should be that if you have a difference, then the sane model is correct.
Mm-hmm.
Right. Yes. So what and it really has this status in an official way, right? So the RISC-V Foundation says that it's still sort of a work in progress, but the plan really is that the sane model becomes the ground truth, the very official ground truth. And they're not quite there yet, because a number of extensions that have been ratified for RISC-V aren't really part of this model yet, but that's the plan anyway. Right. So what I wanted to do now is I wanted to become a little bit more concrete, right? We've been talking about this DSL and that you can use it to specify the behavior of instructions. And so what I wanted to do is to start from the RISC-V instruction set manual. So this is basically the volume 1, the user level ISA. And this is basically a long document that tells you what all the instructions in RISC-V do. And I mean, all the instruction set architectures have such a thing. Like the one for Intel is famously gigantic. It's like thousands of pages, I think. Right. And the one for RISC-V is basically split up in a number of different sections. Like RISC-V exists in different bit widths. There's a 32-bit RISC-V variant and a 64-bit RISC-V variant. There will be a 128-bit RISC-V variant. And so some of the instructions are in all of these, and then there are various extensions which your CPU might implement or not. And we would start with one of the very base instructions because it's small and easy to understand. And here, okay, the manual says something about which registers there are, and here's a diagram that shows you which kind of encoding types of instructions exist. There's an R-type encoding and an I-type and so on. We will concretely look at the I-type encoding, and the I means it has an immediate, right? So it's an operation that has a register input and a destination register where the computed value should go, and then it also has like a concrete number, like 12 bits of concrete number that you can that gets combined with the value in the source register somehow.
And this is from right to left, just to like the opcode is the first thing you would decode, right? And then you would decode, then you would figure out that it's an I type, and then you would decode the rest of the arguments.
Yes. you would look at these 6 bits first, and then you need to find out what the func3 means, and then you have like the 32 registers. That means you need 5 bits to specify which of the registers you mean for the source register here and the destination register here. And then those 12 highest bits are the immediate. Right.
So the immediate means an immediate value that you're doing this calculation on directly in the
right. It's basically if you want to like add 5 or something, like a concrete number, then you would use the immediate encoding to say, I want to add the number 5 to this source register and store the resulting thing into this destination register. Right.
Cool.
Right, and the opcode for all of them is the same, actually, right? So there's a bunch of instructions that take an immediate, and the lowest bits are always op-im, and there's some table somewhere which tells you the concrete bits, and we don't really care which bits are set in that. We just need to know that there is a bit pattern for the lowest 7 bits that tells you that this is an I-type instruction, and it takes, yeah. That determines the rest of the shape of these fields, right? And then there's also a table that tells you that add I has this bit pattern in the func3 in these things here, and then there's and I, like and immediate, or I, or immediate, X or I, and then there are 2 variants of SLTI, and that's set less than immediate, both in an unsigned and an unsigned variant, in an unsigned and a signed variant. And that is used to basically compare a source register with a concrete number, and then write the Boolean result as 0 or as 1 into the destination register.
Okay, and if I look at the Intel handbook, it's very much like this. There's a description of the bits, and then there's a textual description of what it's supposed to do.
Right. Yeah. So I mean, I think that they're kind of a little bit different styles of instruction manuals. Some instruction manuals, like ARM, they tend to have a bit more pseudocode like style, and others just like this one and just writes text. Right? So here we say add I rd rs 0. That's interesting. It's used to implement the move assembler pseudo instruction. So instead of like if you want to move a value from one register to another, you can add 0 to achieve this. Okay, so that's basically the human readable spec. Let's go one level down. One level down, this is where the sale model comes into play. And we don't, I mean, I've been telling you that sale is a DSL for writing down specifications for the behavior of instruction set architectures. And so it's a bit like, what does this DSL look like, right? So that, and it's basically, the DSL is a functional language. It's statically typed, and it has some OCaml influences, I would say, and it has like pattern matching, and then to make it sort of particularly suited for the task of specifying CPU behavior, it has a bunch of features that sort of fit this space particularly well. And one of these features is that it has a bit vector type, right? A bit vector type is just a type, it's called bits. Here you see an instance of that. And bits takes an argument, which is the number of bits that this bit vector type can store. So this would be 12 bits, right?
This is the I type back from the same table. It was the center section there of the
yes, we can compare it. And this is, I mean, so what this type here is, it's an AST, which means abstract syntax tree, which is a bit weird because there's not really any abstract syntax here, and the AST nodes aren't a tree either. It's basically a tuple of information that you need to know what the I-type instruction contains, what kind of information the I-type instruction contains, right? And you can match it to the fields here. I-type has an immediate field. It has a source register and a destination register, and then this func3 thing, and the opcode, you don't need that because you know already that it's an I-type.
Right? Got it.
So it has, I mean, the fact that it's an immediate is basically encoded into the type. Right? So we have the I type, and it has the immediate, it has 2 register indexes, and the IOP. And we can look what the IOP is. The IOP is it defined in here? It's probably some other file. Do you want me to grab for it? I mean, it's basically an enum, and the enum members are these things. It's an add I, then these 2 comparison things, and I, or I, and XOR I.
So there are 1, 2, 3, 4, 5, 6 of those, and if we go back to the table, there were 6 different commands in that table.
1, 2, 3, 4, 5.
4, 5, 6. Yes.
Right, and so that means they're 3 bits. That means there are 2 unencoded ones, and like those could be added later if somebody comes up with a super useful immediate operation that everybody needs now. Right?
The register must be defined somewhere else, because it says those are 5 bits, but I don't see you saying bit 5 there on reg.
So let's actually grab for that. So this is I have a checkout of the RISC-V SAIL model here, and there's a model directory, and it's a bunch of
SAIL files.
SAIL files, yes. And now we need to find out the register index is used everywhere, of course, right? But here we can see it. No, wait, what was it called? Types. Right.
So it's defined as a 5-bit field.
Yeah, right. It's basically some kind of type def, and it says a register index is a bit vector of 5 bits. Right. Okay, so, and then IOP. IOP is this enum. Let's actually look for it. I think it's useful to look at the IOP. I hope this is the way it's spelled. It's in the same file, right? No, here. Right. It's an enum, and it's just a way to give these bit patterns a symbolic name, because you don't want to write 0, 0B0, 0, 1 or something everywhere, right? So these are the enum members, and then there's a mapping between the bits and the enum members, and this is this function. It's mapping that takes an enum member and converts it into the bits, and vice versa, right? So the fact that this is one of the interesting features of SAIL. SAIL has functions that you can run in both directions, and that's nice. What the double arrow here means. This double arrow means you can run encode decode IOP either by giving it the 3 bits, and then you get an enum member back, and then it matches against this side and returns this side, or you give it an enum member and like listed here, and then you get the bits back. And I mean, it's just a shorter way to write this pattern only once, without, like, the other one would really just switch the sides, right? If you wanted to write a sort of more normal function. Right. Okay, so now we know how to map the functions to these enum members. And now we need to figure out how, if we actually have a concrete instruction, how do we take that instruction? And an instruction is just like some bits. We can look at the manual how many bits. Here we see that it's 32 bits, right? So that would be a bit vector 32 in SAIL. And so to decode that, we need to map a bit vector 32 into an instance of this AST type, I type. And that's what the mapping clause encdec is for. I'll talk about what the clause means in a moment. But the idea of encdec is it's encode decode, and it can be used either to take the bits of an instruction and turn it into an AST, like the decoded instruction, or you can also run it in reverse. You can give it the decoded instruction, and it will give you the bits back, right? And so here it says to relate an instance of this I-type AST with the bits, you need to look at this expression. And what the add operator means, the add operator concatenates bit vectors, right? So we know that im is an instance of bits 12, and rs1 is an instance of bits 5, and endcdec iop is bits 3, and rd is bits 5 again, and then here we have this constant. And so if you add all these bit widths together, it has to add up to 32. Right? Does that make sense?
Yes, very clear. So far, so we've gotten from the bits to an actual understanding of how it parses it out to the command with the operands.
Yes. And now, now we decoded the instruction, right? So now we split the instruction bits into sort of more semantically useful things, and that's what the I-type AST is for. And then we can actually execute this AST, right? And so that's what the next function clause is for, and that's execute. And execute is obviously not a bidirectional function. That's just a normal function, and it takes an AST and then it does stuff, and that's actually kind of imperative here, right? Because it really is an emulator, and you have registers in that emulator defined, and if you want to execute things, then the values of some of these registers or one of these registers will change, right? And so to see what the I-type does is first it reads the source register, and that's what this weird capital X function is for. And rs1 is like the every register has a number, so it gives you the value stored in one of these the registers of the machine, and then you have the value of that register. And
so this is an example of the I-type, or this is the actual I-type? Because rs1 could be any other. Oh, I see up above it's also rs1. All the way through, it's defined as rs1, but it could be any register.
So rs1 is 5 bits. No, rs1 is 5 bits, and the bit pattern tells you which register to read from, right? So and that's what the X function does. So if you want to read from the first register in this instruction, then it would be 00001, and then X would go. We can look at X in a moment. X would go.
So it would actually pull the value out of X.
Yes, and X is basically just a big. It's just a big switch. It just says if rs1 is 0.
Yeah.
Right.
Okay. So rs1 val is a temporary value within this function.
Yes, it's a local variable within this function, and that's the number that's concretely stored in the source register of the I-type instruction that we're currently executing.
It's a bit confusing. They call it rs1. It would be better if they would call it rs input or something instead, but whatever. Right.
So I can. It makes a little bit of sense, I think. So the reason why it's rs1 is because it's the first source register, right? And for I-type, there is only one source register, but for some other instructions, there's rs1, rs2, and then
rs means register source. I see.
Yes. Okay. And then the rd is register destination. Yes. Right. So we read the value of then we have rs1 val, and then we need to take the immediate. Immediate is 12 bits, and then the manual said, let's actually find that. Right. Add I adds the sign extended 12-bit immediate to register rs1. Right. So here we take the immediate, which is 12 bits, and then we sign extend it. And so XS is sign extend. There's also X0, which is used here, which is 0 extend. And the result of that is stored in imExt. And here we have we see the type of imExt. ImExt is of xlen bits. And xlen bits is either... Yeah, go ahead.
The typing here is much like Python typing, where you have a colon and then the type.
Right. Yes, that's what the syntax looks like.
Python took from somewhere else, probably from OCaml in the first place.
Yeah, I don't know. My OCaml is terrible. So xlen bits is defined to be a bit of 32 bits or of 64 bits or of 128 bits, depending on which of the variants of the RISC-V architecture we're running. Right. So that's again defined in one of the header SAIL files. So we turn the 12 bits into 64 bits, for example. Then we compute the result, and to compute the result, we pattern match on the op. The op is one of these enums, and then if it's an add I, then we will add the register 1 value to the sign extended immediate, and that gives us the result. And then there are other cases for and I. We use a bitwise and on the immediate and the value, or is or, an XOR, and then here is the case for these comparisons which returns a bool, right? Mm-hmm. So this one gives you is a signed comparison or an unsigned comparison, and it returns a bool, and then you can return the bool. You can convert the bool to a bit vector of width 1, and then you can zero extend the single bit to 32 or 64 bits, and that's your result.
Sure.
And then the last thing that you need to do after you computed the result is actually store it into the destination register, and you do it with this kind of syntax. Right.
Sure. And so then, this is all valid OCaml. We could just run this if we wanted to put together a.
It's
more of a program than ESL, isn't it?
Right. It's not really OCaml. I mean, I think it takes some inspiration from OCaml, but it's really its own language.
Okay.
SAIL, right?
So we don't actually have a downloadable parser for this that would run it. I'm leading with the next question, right? We want to be able to run this in some form.
Right. I mean, so now we have this, right? And we only looked at a tiny bit of it, but we looked at what does it take to actually run one of these instructions, add I, and so it's written in this DSL, and the question is, what do we do with a program in this DSL, right? And this DSL has a bunch of backends. And one of the backends is it can actually produce proof statements in a number of proof computer-aided proof tools like SMT solvers, or can also output COC, which is another tool to do computer-assisted proofs. And so that's more the formal side of things. But yes, I mean, your question was indeed leading. We can also use this to produce an emulator, right? Because this does look like sort of functional / imperative code that you should be able to just take and execute. And if you execute it, what you would get is a concrete way to really take binaries compiled to the RISC-V ISA and then run those binaries. And that's another one of the backends that SAIL has. It can take an ISA specification in this language, and it can turn it into either OCaml code, and then you can just run the OCaml code, or C code. You can run the C code. And these binaries that you get in that way are emulators for the CPU that you specified.
But then I would still need to compile a program to this language that could then be run by the emulator.
So, right. So, I mean, the emulator gives you something.
I mean, if I want to write hello world, I would need to convert that into the opcodes that would that would hit this emulation.
Right. So if you want to actually print something with the emulator, you would have to write a C program and use a C cross compiler that produces a RISC-V binary, and then you can use the emulator that you get from this file, and that emulator runs the RISC-V binary, emulates a CPU that executes this RISC-V binary, and it would print hello world. Right.
Cool.
Right. And so what we want to do now is we want to descend through the layers, right? This is the DSL, and the SAIL compiler actually takes this DSL and it produces a sort of intermediate representation. And this intermediate representation just it's after parsing and after type checking and after some number of optimizations. So it has a much simpler syntax, and all the complicated pattern matching has been compiled away and so on. And that's called JIT. I don't know what the abbreviation expands to. but you can sort of basically take that and pretty print it and turn it into a string, like a file again. Right? And this is this thing, and it starts with like all the enums that the Sail program contains. For example, here's our I-type enum IOP. It prefixes everything with a Z, and that's why everything is Z IOP here and Z RISC-V I and so on. And then here's the Z AST, and it should have the Z I-type somewhere, right? And here we see that Z I-type is a tuple made out of bit vector 12, bit vector 5, bit vector 5, and then an instance of this enum. And then we can look what happens, like what else is done with this I5. Let's see what function that is. Right. And so what we found here is the part of EncDec that takes the bit patterns and produces an instance of I-type, right? So this function corresponds to this thing here, which takes the bits and produces an I-type instance. Right? So lots of complicated stuff with relatively sort of straightforward syntax, but pages and pages of the stuff. And at some point, we found out that, oh, we do indeed have an I-type. And here we see
just the name of this function was something jump forward, backward. That's the mapping. That's the two-way mapping.
Right. It's the EncDec backwards. So it's the version. This gets compiled into two functions: the forwards function and the backwards function. And we saw the backwards function, which takes the bits and produces the AST.
Okay.
And so on the JIT level, these bidirectional functions don't exist anymore. It gets basically split into the forward version and the backwards version. Right. And so the backwards version takes the encoded instruction and produces an AST instance. And here is where the instance is produced. And then we go to something, and then I suspect that we just return this thing. Right. Okay, so that's one level down. That's sort of the intermediate representation, what Sail uses. And then from that, it actually makes C code. We can look at the C code briefly. I mean, as usual, like generated C code is scary. So we can see whether we can find the enum. Here's the enum. And then we can look for I-type.
So the input to the C generator is the JIB IR.
I don't completely. Yeah, that's a great. I don't completely know what the architecture looks like. It's my understanding,
but it comes from the DSL. This is C code that's been generated from the DSL.
So it's my understanding that C code is not directly generated from the string version of JIB, but there's also an internal data structure version of JIB, and the C backend uses that, like just to start from that, right? But it doesn't produce the string on disk and then parse that again or something like that.
And then the result of compiling this, again, is an emulator that, given a RISC-V compiled binary, will uncompile, will take that binary and run the opcodes and actually do whatever that binary tells it to do.
Yes, and it's basically an interpreter for these binaries. It's like, I mean, QEMU can do this too, right? QEMU can run ARM binaries on your x86 host CPU, or RISC-V binaries on your x86 host CPU. And I want to try to find something here that relates to what we looked at so far. But I'm finding lots of switches where every case about I-type says do nothing. Okay, let's actually try to find EncDec backwards. Right, so that's here. That exists. And it's scary. And maybe we can see
case function.
Yes. And maybe we can see whether we can find I-type somewhere. Right. Here's the constructor, right? So there's stuff happening.
It's taken that map and turned it into an enormous switch.
Yes.
And if it hits case 9209, it will go and say, okay, this is an I-type.
Yes, it will produce an I-type AST instance, which is a struct, basically. and then it will return that. Right? And then there's also the code that runs that somewhere. Should we hunt for that, or are we happy with this?
No, I think we're good.
Okay. Right.
We
Okay.
haven't actually gotten to like where we want to be. We haven't started with what's interesting from a perspective of Pydrofoil.
Right. That's true. Right. So we'll have to talk about Pydrofoil really soon, but let's actually finish the sail bit. And so we have this C code somehow, and you can take the C code, and then you will actually get, I think, wait, where is it?
I think it's called sail dash something.
Here, it's this one.
Okay.
It will produce this binary, and this binary basically takes RISC-V programs, like RISC-V ELF programs, for example, and it will run them. And it's quite complete, right? It emulates like all parts of the system, like of a RISC-V system. It has privilege mode and user mode and switches between the modes, and it does page table walks, and it emulates everything, and it's complete enough that you can do something like boot the Linux kernel on it. And I'm starting that, and it's slow, and now the bootloader booted Linux, and then now it will start booting Linux on the emulator, and it takes like an hour, but it works. Right.
So if I would take that same binary blob of image of Linux and run it on a RISC-V chip, I would actually see this output.
Right.
Or something close to this output. Maybe there's a little more debugging stuff, but
right.
Yeah, I see their Linux version 4.15.0.
Mm-hmm.
It's actually booting a Linux kernel on top of this emulator running on your laptop, which is an x86, whatever.
Exactly. Yes. Right. So that's background. Now we need to talk about our project. So as you already can see here, like if you put Linux on QEMU, it takes not a lot of time, a couple of seconds, right? If you do it on this one, this emulator, it takes like literally 70 minutes on my laptop. And so we already see that this is very slow. And it's slow because the abstraction level is so high, right? It's slow because the description of the ISA is not really at all concerned with how do you execute this stuff quickly. The main reason why the model was written is how do I make sure that I don't have any behavior bugs in it. And so the fact that you can actually use it to emulate things, that's sort of a nice side effect. But that's not really the main motivation. And because the abstraction level is so high, we get an emulator that is sort of hopefully very correct, but very, very slow. And so that's where we come in. I mean, so that's what my friend Martin challenged me to do is take this very high level, but hopefully very correct specification of the behavior and turn it into a fast implementation. Right. And that's what the Pydrofoil project does.
Just the begging the question of, well, then why don't we just do what QEMU does? Because then basically we're throwing away all of this vast knowledge we have about the correctness of the model, and we're just cutting it down and saying, we're going to stick with this one model that we know, and we're going to optimize it. But actually, if someone changes the model or adds another feature to it, then QEMU would no longer work properly.
Right. Yeah. I mean, so one idea is indeed that if you like want to experiment with a new extension and you like specify a bunch of new instructions and you specify the behavior and stuff like that, then you would just do it in the Sail DSL. You would like go here and you would edit this file and add a bunch of new bit patterns and do something very experimental. And then you have a problem because in order to actually run a program that uses these new instructions, you would have to specify the behavior of them in a second place, which is QEMU or another emulator. Right? And so the idea would be that if we can make these emulators generated from the nice high-level model faster somehow, then we would only, like when we could do experiments more quickly because we would only have to specify the behavior in one place, and we need this place anyway to do our proofs or something. Right? And so, right, so the goal is we take this model and we produce a fast emulator from it, no matter what extensions were added to the model, right? And the goal would be, the goal is to use all the machinery that we have implemented in the last, I don't know, how old is PyPy again, Matti? 2003?
Almost 20 years.
Almost 20 years, right? It'll be 20 years in fall or something. Wow,
yes.
Next year. Right, so we want to take all this whole tech stack, and it has lots of stuff. It has a JIT compiler infrastructure, a generic one, and it has optimizers and backends, and it's battle tested over a long period of time. We want to take all this stuff and we want to reuse all of it in order to make the emulators that you can generate from these sail models much faster. And that's the goal. And we do that by basically adding a different kind of backend to Sail. And so Sail, I said before, Sail has a backend that turns the model into a proof. It can take the model and produce an emulator written in C. And now we added a new backend, and that backend takes the Sail code and it turns it into RPython, right? And so RPython is the implementation language of PyPy. It's a restricted subset of Python. And we start from this IR code that we looked at earlier, which did all the complicated front end part and type checking and so on. And it only has very simple-ish low level operations left that do not very complicated things. And so we parse that, and then we take this code and have a little compiler that takes this stuff and turns it into RPython code. And so we can do this for the same thing, and you get this file. And now, I mean, we very briefly looked at generated C code. I mean, I fear that I have to tell you that generating Python code is not really any less scary, right? So this is a 200,000 lines of generated Python code, and it's quite scary. But we can try to find the landmarks again that we looked at earlier. So we can try to find the enum, right? So the enum here is just a class, and it defines a bunch of class attributes. And then we can also look at itype, right? And an itype is also a class, and it's a subclass of a base class AST, and then it has a bunch of fields, and the fields are a bit vector with 12 bits. That's the immediate bit vector with 5 bits. Another bit vector with 5 bits, and an IOP. And we don't even have any types here. It's just 4 fields that have numbers, right? So that's all kind of implicit.
But somewhere along the line, the RPython code will know what these types are. These are typed, just they're not explicitly typed at this point in time.
Yes.
Just like 5 lines up, there's an explicit type.
Yeah, there's an explicit type that's just a comment for me if I want to see.
Up maybe 10 lines up at the beginning of the class, just where you are at that class. Sorry, there's class union zast, and then there's utop 0 equals ruint 0. That ruint means
those are the default values. You're right. Here you can see that the first 3 are bit vectors somehow, and then the third one is weird. It's an enum is just a number, and negative numbers are invalid enum. So I'm initializing it to something invalid, basically.
Mm-hmm. And just there was a program that converted the JIB into C, there is now a program that converts JIB into this Python code. This is all generated.
Yes,
in spite of it looking like very nice Python code.
Well,
comments.
Hopefully you never have to look at it, right? I mean, if things go right, you never have to look at it. So there's here we are at the encdec backwards function again. Mm-hmm. And that's the function that takes the bits that specify an instruction and turns it into an AST, which is like the decoded instruction. And here we run into the first problem. The first problem is that Python doesn't have gotos. right? And the JIT code and also the generated C code uses gotos all over the place, right? So what I'm doing here is I'm emulating gotos with this weird construction. It's kind of standard. That's how you emulate gotos if you have a language that doesn't have them, right? So the labels are basically an artificial PC variable, and that just says, where should I continue next? And so PC doesn't have anything to do with the PC like of the emulated CPU. It's just a way to do jumps. And so this means go to label 0, and then here's the label 0. And then at the end of that block, we set the PC to where we should continue. Right? And then we go around the infinite while loop, and then we eventually end up here. Right? And this looks terribly inefficient. And if you just run this as normal Python code, it is terribly inefficient. But we have been using this pattern in RPython in the past. At the moment, we are not really using it in PyPy anymore, but we have, like 10 years ago or something. And so that means if you take this Python code and use RPython to translate it to C code, you will get exactly the same labels back because we do enough work to get rid of this stuff. Right? And so that's just a side note. That's how we get gotos in a language that doesn't have gotos.
Okay, but before we saw an enormous switch. So this is basically that switch.
Yes, absolutely.
Using ifs instead of cases.
Yes. And here's the construction of the I-type, right? This is the branch where we decided that, it's an I-type instruction, and we extracted all the bits with this scary looking code above. And then here we call the constructor of I-type, and then we jump to the PC that says, return this thing, right? So this is, in some sense, this is just another form of what we saw before, right? It's Python code, and now we can take the normal RPython and PyPy machinery to take this type, like statically typable Python code, and turn it into C code.
But again, just like with the C code, this is used to build an emulator that will then take a RISC-V binary and run it, and take that binary apart, opcode by opcode, and run each opcode. Absolutely. It's not actually running this as a program. It's compiling this into an executable, and that executable is the emulator that will then be used to emulate the RISC-V.
Yes. So this whole mess, it's like as I said, it's 200,000 lines of code. It's a big mess. We take this big mess, and then in the end we get another binary. I mean, it's also a binary that the C compiler spits out, but just going a little bit of a detour via RPython, and it behaves basically in the same way, right? We can also take, I mean, that's the whole idea. It must behave in the same way. We can take the same arguments and also say, here's the Linux image that we should boot. This, by the way, it tells it how many instructions it should go into the boot process, and then after that many instructions it should stop. And I mean, doing any kind of timing while streaming is always a bad idea, but maybe we could see that the bootloader logo appeared a little bit more quickly. Right? So in order to execute these 2 million instructions, it took 13 seconds. If we're adventurous, we could leave the original Sail emulator running.
Yeah, I think you need minus time there somewhere.
Oh yeah, you're right. I will just do this instead.
Yeah.
Right. Yes. The lines of the logo take a bit longer to appear. And
yes.
Yeah, so the speed up for booting Linux is about 18x, right?
18x.
Right. Yes. But we don't really understand where the speed up comes from yet, Matti, because so far the story has only been, okay, we have Sail, we can turn it to C in the normal way, or we can turn it to C code in a slightly weird way by going via RPython. But I mean, that's not really what RPython is about, right? Now we get to the extra trick that PyPy has, that RPython has, which is that if you have a program written in RPython, or in this case generated in RPython, we can get a JIT compiler for that interpreter, right? So
yes, this is the important part, and we've gotten to it after 45 minutes. So
yes,
yeah.
sorry.
We're both guilty by this, but yes, I mean,
right.
Often, like I spend so much time fixing bugs in PyPy that I rarely get to the point where I can appreciate the JIT, and it's just such an amazing, really, piece of technology that you write this code in this restricted Python language, and boom, you're automatically given all these other things.
Right. And the thing that we're automatically given here is pretty cool, because so let's think about the implications. So what I've been saying is we have an RPython program, and the RPython program, we generated it in a slightly weird way, but this RPython program is an interpreter for RISC-V binaries, right? I mean, emulator is just, I mean, it's an interpreter, right? Like the terminology is slightly different when we're talking about a language versus a CPU, but that's what an emulator is. It takes bits for instructions, and then it turns them into behavior, and right. And so RPython has a generic JIT compiler that works on sort of arbitrary interpreters, and you can apply the PyPyJIT to arbitrary interpreters written in RPython, and then you get a JIT compiler for the language that is running on top of that interpreter. So, and when we apply to PyPy3, for example, we get a JIT compiler that takes Python 3 code and turns it into machine code at runtime. And we can apply the same meta-JIT to an interpreter for Python 2, and that means it will take Python 2 code and turn it into machine code at runtime. And now we have a third language here, which is we have an interpreter for RISC-V binaries, and that when we apply the JIT to that, it becomes a JIT that takes RISC-V binaries, which are themselves machine instructions, and it will turn those at runtime into machine instructions for the host architecture. So it basically does binary translation. It takes the RISC-V instructions and then compiles them at runtime into x86 instructions and then runs them. And that is much quicker than sort of looking at the bits of our add-I instruction every time we want to run it, right? If you have a loop, like let's say a memcopy or something, we have like 7 instructions that we just repeat 10,000 times. And every time the standard Sail emulator will reanalyze the bits again and again and again. And with the PyPyJIT, we get rid of all of this. We will analyze, I mean, in the beginning, we will still start sort of with an interpreter, but after a while we say, okay, I've seen this loop a bunch of times before. It makes sense to like make much faster code for it. And then we take the RISC-V machine code loop, turn it into an x86, a machine code loop, emit that into memory. And from then on, we can run the x86 machine code in order to get the behavior of the input loop in RISC-V instructions. And from then on, it doesn't have to redecode every instruction and again, because every instruction has already been turned into x86 instruction, and it can just run that.
So if we go back to the standard and look at that same instruction we were looking at, JIT will take those, it'll take the opcode and the destination and the source and the function, and maybe even the value if it knows what the value is, and will already execute that in one step.
Yes.
Rather than trying to take it all apart and look at which register it should work on and which opcode it needs to work on and which function it needs to work on.
Right. So it will already hard code, like when it translates a concrete instance of an add-I instruction, it will turn that into x86 instructions that hard code the source register and the destination register and hard code the immediate. So the immediate will probably turn into an immediate on an equivalent instruction in x86, right? The source and destination register are a little bit more complicated because in the emulator they aren't machine registers, right? They live somewhere on the host heap, right? So there will have to be some extra instructions that load the registers, but there's actually some nice optimizations in the JIT going on too. So if you have a bunch of instructions in a sequence and one of them loads stores something into register 17, and the next one loads from register 17, we can actually map this to an x86 register, and then have less movement back and forth from the heap on the host. Because the RPython JIT compiler will also do cross instruction optimizations. It doesn't compile one instruction as its own entity. It takes like a whole bunch of them, usually like one loop, and then it optimizes them together and tries to sort of do constant folding and all kinds of classical compiler optimizations to try to get this stream of several instructions to be as efficient as possible. I mean, this is a really hard task, because the abstraction level of the Sail language is so high that there's a whole bunch of nonsense that the RPython JIT needs to get rid of first, right? So,
but correct me if I'm wrong. In most of these loops, in our Python or in the Python JIT, there's a concept of guards that will guard against invalid variables or variables that it didn't see the last time it executed the loop.
right.
Here, the chances of that happening are lower, I think, than in Python code, where Python you can throw arbitrary objects around. Here, there's much more structure to the code, and the guards, they're going to be very, very fewer. They're going to be many less guards than there will be in Python code. So
so what Matti is referring to is that if you apply the JIT to Python code, we bake into the generated x86 assembly all these assumptions about the types of your variables, and those assumptions get turned into guards, which are small checks that, oh, is the type of x still an int the next time I run it, right? And if it is, then we can stay on the fast path that we made machine code for, and if not, we need to go back to the interpreter. And of course, RISC-V assembly isn't dynamically typed, right? So there are none of these type guards. There's still a few guards. There are guards like, oh, is the memory access that I'm trying to do here, is that aligned? And if it isn't, then I would have to do some kind of fault and jump to a fault handler, right? And so, because most of the memory accesses will be aligned, that still sort of gives you a sort of a fast path kind of behavior, right? But I completely agree that for Python code, you usually have like a bunch of guards everywhere, and in the code that you generate from RISC-V input programs, you usually don't have any guards, right? Only for stuff like, is it aligned, and like did the timer fire, right? I mean, there are asynchronous interrupts, which means that every n instructions you jump back to the OS, and so you need a guard for that kind of stuff. But that's not actually what I meant by having lots of sort of slow and complicated stuff to remove. The problem really is that the Sail input program has a whole, like a huge amount of things that happen to make it nice and readable and abstract. And in order to sort of get any kind of performance back, you need to really aggressively optimize all of that. And I'm not really sure we can see a lot of them for this instruction. For example, it might be interesting to see what XS is. Let's actually try to find that. So XS is a zero extent, right? And so that's kind of interesting. So here we see the type, and it's implemented by some kind of internal call. But the type of it is, it takes an integer and returns a bit and a bit vector, and it returns a bit vector. And the bad thing about these types are, here it's not a bit vector 12, it's a bit vector of arbitrary size, right? Because Sail, I mean, in Sail you can also write, I want a 10,000 bit vector, right? I mean, in practice, it's mostly like a small bit vector, like bit vector 12 or bit vector 64 or something small. But this function here takes an arbitrary bit vector. And if it's an arbitrary bit vector of an unknown size, it means it will be stored on the heap. And that's expensive because it means to store on the heap, you need to call malloc in C. So if we look at the C code for this sign extension function, I mean, here's a call for it. The context doesn't matter much. But what happens here is we create an lbits thing, which is an arbitrary size bit vector, and that calls malloc. And then we call it with a number of arguments, which have themselves been malloced. So here's a conversion function from finite bits to arbitrary sized bits. That's another malloc. And then we have the result somewhere, and then we have to convert it back, and that's a free, right? So even the simplest arithmetic function that just takes bits and sign extends them involves like calling 2 mallocs and 2 frees. And that's also the reason why the C code is so slow, because it all the time I mean, if you look at the profile, all it does is mallocing and freeing these bit vectors that could be arbitrarily large, and in practice they aren't. In practice, it's basically always 64 bits or 32 bits or like 12 bits here and there, or at most 128 bit, but never much bigger. But the C code has to be prepared, or at least it couldn't know ahead of time that the bit width is actually some small and easy number, right?
So this is an added optimization that RPython gives us for free that C can't actually do unless someone sits down and says, okay, I know that 90% of the time there's going to be small allocations here. Let's do something a bit different with the code that's generated by sale.
Right. But we just get, you're absolutely right. They could work a little bit harder to also get a similar effect of not having to malloc that much. But they don't, and they do call malloc a lot. Sorry. Let me actually grab a mint. I'm back in a second.
Someone has started watching us.
Back. Right, and in RPython we get this for free, because the reason is Python does this a lot, right? In Python, every integer is allocated on the heap. And that means that we are perfectly prepared for to optimize programs that allocate a lot and free a lot all the time, because every Python program does that. And the fun thing is that this emulator, because it's so abstract, actually does much more of it. So in Python, if you have an add in like an add bytecode, it will like allocate 1 int because that's the result. But here you have all these intermediate steps of like splitting up the bit vectors and extracting small parts and zero extending stuff and sign extending stuff, and all of them allocate, right? So here per RISC-V instruction, we do lots and lots of mallocs. I think I measured something like 30 mallocs per instruction. And that's what I meant when I said that the JIT has to work really, really hard to get rid of all of them. In the end, it does get rid of all of them. And you do end up with reasonable like target code. But there's a lot going on to actually reach that state. Oh, hi, Anthony. Good to see you. Right. So yeah, I mean, I think that we're basically through most of it, Matti, aren't we? Like we should.
Sure. I mean, we spent a lot of time warming up, and then we activated the JIT and talked about that for like the last 10 minutes, which is probably appropriate for a discussion about PyPy and the JIT. We had a long warm up and then a short discussion about what makes it all fast.
That's true. Right. Yeah, I mean, I'm of course perfectly happy to talk a lot more about the JIT, but maybe we can do that guided by questions. So, is there anything we like? I'm asking the chat. Is there anything we should talk about specifically? I want to do the demo a little bit.
We did want to look at the website of Pydrofoil.
Oh, yeah, right.
and
Right,
just
absolutely.
see what we've documented about it.
Right. Yeah. So recently, Matti and I have been trying to, like, as I said, this project started in summer, and so in the beginning it was just a big pile of hacks, and so in the last couple of weeks we've been doing a lot of like sort of foundation work, and so now we have some proper GitHub actions that test all of that stuff, and that's one thing we set up, and like the action will produce a binary and then boot Linux and check that it works. That's the wrong action. And then the other thing we did is like have set up a read the docs page that explains a little bit how you would use all of this stuff. And like,
could you make that a touch bigger?
Oh yeah, I also want to like paste the link into the chat. Where's the chat?
Mm-hmm.
Here. There you go. Right. So the docs, it's not super deep yet, but it basically tells you how to build it. You can also grab a binary if you're on Ubuntu or on an x86 Mac, you can grab a binary from the GitHub Actions too. We also want to do a binary release very soon. And then there's some hints, right? There's a page for how to build it, a page for how to use it, like booting Linux on it. There's some internal hints for how you do stuff when you actually want to get involved and want to like work on the source code of Pydrofoil itself. And I'm also in the process of like sort of adding a bit more explanation to how it actually works and what the optimizations are that do the important stuff. So QWERTYface asks, how does the performance compare to handwritten emulators like QEMU? And that's a great question. I mean, so at some point I said that one of the motivations for doing this stuff is that if you experiment with a RISC-V extension, for example, then you don't want to have to specify the behavior in two places, in the same model and in QEMU, right? But of course, this only is a viable approach if you end up with something that's sort of comparable to the performance that QEMU gives you. And so we did a little bit of early benchmarking on that. So on some of these, actually, can I find the numbers? Let me actually try. So I'm going to search for the PDF and then I'll share again. So the early numbers are something like on some benchmarks we are sort of in the right order of magnitude than QEMU, and the other really fast emulator is called Spike. That's also sort of officially maintained by the RISC-V sort of ecosystem. And for some benchmarks, we're in the same rough ballpark of these. But then for others, we're sort of still 100 times slower than them. So we're not there, right? It's still a work in progress. And we certainly like we get a lot of speed up compared to the very slow Sail one. But yeah, I mean, it's partly because the reason why we get such a big speed up is partly because the baseline is so terrible, right? So then if you compare it to something that's actually good like QEMU, there's still a way to go. And I found some numbers, right? So this is really terrible benchmarking. It's just like 4 micro benchmarks and Linux to boot. And this is basically the speedups of our implementation, and this is the important column, the speedups of Pydrofoil compared to the Sail-based RISC-V emulator. And for some of them, like Drystone, which, yeah, awful benchmark, but it was easy to get run, it's like 1,000 times speed up. And then for some, it's only 11 times. Towers, that's another small micro benchmarks, and I don't completely understand the difference yet. I understand it a bit, but it's only 11 times. And then for the ones where we're really, really fast, we also compare sort of okay against Spike and QEMU, right? So for Drystone, we are at sort of roughly the same speed as Spike. So Pydrofoil is green, Spike is red, and QEMU is yellow. And yellow is actually slow. QEMU is actually quite a bit slower than Pydrofoil. But then for the others,
Hydrofoil is faster than QEMU for this particular benchmark.
Yes. So that, I mean, this is where we want to be all the time, but we're not there all the time yet. So QEMU still handily beats us for this weird integer matrix multiply tiny benchmark, where QEMU is still like 10 times faster at least. And then there's one where we are, I mean, it's also interesting that the handwritten emulators are quite different in their performance profile, right? There's a 5x difference between Spike and QEMU in both directions depending on the program. Right? But for some things, I mean, Spike and QEMU still completely like defeat us.
Blow us out of the water.
Yes. And I mean, I have some ideas, and I'm working on like the next thing. But yes.
Do you have any idea how much effort QEMU has put into the Spec5, the RISC-V emulator?
QEMU has a really, really excellent architecture because it actually does share the effort between the different front ends, right? So in QEMU, you have an intermediate representation. It's called TCG, I think, or something like that. And that's basically sort of an intermediate target that you compile your RISC-V instructions to. And then there's a bunch of backends depending on the host machine that you're on, right? And there's also some optimizations that works on this front-end independent intermediate representation. So it's not that hard to like add new instructions to QEMU for whatever instruction set architecture. Basically, you take your instruction and you need to decode it, and then you compile it into this set of shared abstractions that all the front ends can sort of reuse. But yeah, I mean, and then they share all the good backends that they have, like instruction selections for various like host machines and some optimizations. But I don't have a number. I can't tell you whether it was like years or it's probably years, right?
At the end of the day, our Python also has numerous backends.
Yes. Right.
And so does the C compiler, basically, the C code from Sail.
Yes. I mean, what I've done so far wasn't a lot of work, right? I mean, the whole project started in like June, and it's not like I was working full-time on it. It's been a side project for most of that time. So I would, if I have to like estimate it, it's probably been like between the two of us, like 3-4 months of work.
Right.
So it's still very young, and it wasn't.
You had a student too, right?
Yeah, John was doing, but not scary amount of work. John is also another postdoc. He's not a student.
But I think the important thing here is that basically your work was to take this spec and to have it parse the spec and make our Python code out of it.
Yeah, I mean, in some sense,
the book and going through the book and saying, okay, this is how this looks. Let's handwrite a front something that will parse this into IR.
I mean, in some sense, I didn't do any of the hard work on either side, right? Because I didn't have to do like I've been taking the very carefully written explanation of what RISC-V instructions do that already existed. That's the same model, and I've been that's the front end part. And I've been taking all the machinery that PyPy and RPython has developed, and I've just written a little bridge between the two. And if you combine them, and that wasn't necessarily clear in advance, but it turns out that if you combine these two things, you get a relatively good, you get something that wasn't a huge amount of work, and you get a relatively fast emulator that is complete enough to boot Linux because we've been reusing the front end part, and it's relatively fast because we're reusing the back end part from PyPy. Right. Yep. So that's it. That's the story. Please ask more things. Like anything we should look at in particular, or Any other demos you want to see? Let's start another boot process.
I think it was 1 minute and 10 seconds, right? 1 minute and 7
Yes.
seconds.
I think
67 cents?
the first 2 million instructions we did with both. It's 1 million and 10, so that's 17 seconds. And on PyPy it was 13 seconds. So it's not quite a 20x speed up, but it's also not really, I mean, as I said, benchmarks while streaming is not a thing.
Yeah. On your laptop.
Yeah, my laptop is really old. The other thing we should do is we should actually get it, we should actually run it and have it complete till we get to the login prompt to show that it actually works. That's another 0, I think. No, 2 more zeros. That's a bunch of minutes, right? We will just leave that running, and we can like answer more questions if there are any. I mean, actually, at the end of the boot process is when the really complicated stuff starts, because at some point the first like init gets started. That's the first user mode process, and then things get even more expensive to emulate, because in user mode the MMU is turned on, and that means, I mean, memory protection gets turned on even earlier, but for user mode you have virtual memory. That means you need to emulate the page table walks. And for every page table, that means for every memory read or write, you need to like descend 3 layers of page tables in this kind of mode, and that's when things become really quite slow. And the JIT is, I mean, that's also definitely an area where we should be able to still do quite a bit better. Actually, it's also the case that sort of booting Linux on this thing is not really perfect for the JIT, because like booting a kernel is a sequence of steps, and every one of these steps has some code, but it doesn't run for ages, right? There aren't any sort of, in this step, there might be some helper routines that get called that other steps also call, but there's also step-specific code that just gets run once, right? So actually booting Linux doesn't benefit a huge amount from the JIT, because only a little bit of the kernel code gets actually executed sort of consistently often enough that you will turn it into host machine code. So for the boot time of Linux, the 20x we get on that, it's actually mostly that our bit vectors use, like, we talked about this for a bit, are implemented using dynamic typing and like all the tricks that and all the improvements that we have implemented for like Python, because in Python you can also have integers of arbitrary size, but in practice your integers tend to be only 64 bits. So there's a lot of fast paths and a lot of tricks and optimizations to make sure that such a type is efficiently supported. Right. So we'll just leave this running. And so anything else that people would be interested in? Otherwise, I'll go back to the website, because that's like...
And for people who are deeply interested in this whole idea of emulation and whatever, there are some links there about learning more about Sail itself, and about how these emulators work.
It's like, if there's a huge, I mean, I'm really new to this. I never did any kind of hardware thing before. Matti, you have, right?
I did a little bit of FPGA programming with HDL, and that's actually what got me into PyPy in the first place, was watching my HDL and how much faster it could simulate HDL code than other things.
So my HDL is like an HDL tool chain that also lets you like emulate HDL designs, and it's based in Python, right?
Yes. Yes.
Right.
So rather than writing in Verilog or other HDL, you would write in Python, and then you would produce HDL code, and you want to simulate it just like this. You want to simulate it to show that it's fast, to show that it's correct. Sorry, you have a golden result that you write in Python, and then you generate your code, and your FPGA then runs that code.
Right. But this is an emulation that really that's really a level down, right? It's that's really concerned with the gates and the hardware implementation logic, correct?
Yes, yes, and like the RISC-V code, it has variable length integers, which bit, they have these bit length integers that are they're also.
But then when you actually produce a design that runs on an FPGA, you probably have to infer the width of all of them, right?
Because so the back end will produce the actual FPGA code. So the back end to my HDL will generate HDL code that can be then compiled by a regular compiler into into a binary blob that's then loaded into the FPGA.
Right. Yeah, I mean that's already way deeper the stack than I ever got. I might have to like descend there at some point, right? But there's tons of there are tons of interesting things here. I learned like a whole bunch of very interesting things. Like I've written an ELF loader and understand more how the ELF format works now, and I've been learning more about. Do you know what a device tree is, Matti?
Sure.
Right. I never encountered that concept. So
it's also a text file, right? That specifies the actual registers that you use when you're using either any kind of bus, a USB bus or a PCI bus.
Yeah, it tells you how all the. I can show you the one that we're using. It tells the operating system where all the devices are and how to talk to them.
Yeah.
Is it?
I think it lies on top of a spec, so you need a spec for the actual layout of the buses, and there's negotiation that goes on that's a bit tricky sometimes.
Yes. Right. So I had no clue about any of this. Wait, where's this one? Right. This is what the text file looks like. And basically this gets compiled into a binary blob, and that gets put into memory during boot process, and then the operating system will look at this blob and interpret it in order to figure out how to like talk to the peripherals. And so yeah, that was another fun thing I learned.
Yeah, but there's a bunch of assumptions in here about things you already know about. Like here, the MMU type will be a specific type, or
yes.
So there's a lot of domain-specific knowledge that goes into one of those.
Right. And yeah, and there's also fun things to do, right? So, I mean, the sale model that's sale. Where's the RISC-V model? The RISC-V model is also lacking some of the already ratified extensions. So, like if somebody's interested in the sale part, or like the RISC-V part in particular, there's definitely interesting work that can be done here. So, like for example, there's a bit manipulation extension that adds stuff like set some bit, except the 7th bit and stuff like that. And that is ratified, and it's also already being implemented in hardware. But the specification, like this formal model's ISA model, lacks the extension. And so if you want to like dabble with this DSL, that's one thing to do. Right. So, right, if there are no more questions from the chat, I think we should slowly wrap up.
Yep.
Right.
And just want to show the boot prompt if it's come.
Oh yeah, maybe it's there. Let's actually wait for that. So we are in user mode in user space already. So it has started in it, and it will just be another minute or something until it shows you a login. And we can't actually log in because I didn't. I mean, the emulator only supports terminal output but no keyboard input. So and I don't know the password because it's a binary. It's a Linux binary that's just committed somewhere, and nobody. I mean, I don't know who built it, and I don't know what the password is or anything. So I couldn't log in anyway. Right.
Cool. I think by streaming, I think we've killed the performance on this. It's probably like choking on memory. It's swapping all over the place.
Yeah, no, it's not that bad. It should get there fairly soon.
Well, we timed it at 4 minutes once.
I don't. Do you remember when we started it though? I don't. I didn't look at the clock at all.
It was Yeah, it was.
Yeah, it's not too important. At some point, like at some point, it gets to the login prompt. And if you try it, I mean, on Matti's desktop, it also doesn't take 4 minutes. It's more like 2 and a bit. Was it?
Under 2 minutes.
Oh, under 2 minutes. That's right.
Yeah. Well, you've already got a valid file system up.
Yeah. Well, there is no file system, right? So.
Right.
But it has a random number generator and a network that doesn't work because there's no emulated network cards either. So.
Yeah, that's certainly not part of the ISA specification.
Right. Yes. Yeah. And actually, yeah. But
there
here's
you
the
go.
prompt. Right. And that's actually one of the things that I'm trying to get these, like the people that build this and use this, I'm trying to tell me, like, do they need emulated hardware? Do they care, or is that something that they don't care because they only run like these tiny test binaries without an operating system? I mean, that's one of the things that isn't entirely clear to me yet. It's like, is it like, what would a very typical use case of this thing look like? Would it be, oh, I have an implementation and this golden model, and I run them in lockstep and compare them? Is that the main thing to do? Or is it also stuff like, I invented a weird extension and added it to the model, and now I want to run a bunch of experiments to see whether it helps for real software that I care about.
And I'll go into my pet peeve about PyPy, which is we never know what people are doing with it, and yes. We probably never will.
Right. Sometimes people tell us.
Yes. So if you're watching this and you're using PyPy technology or Python or PyPy, and you're happy with it, please let us know.
Right. Okay. I think we're wrapping up. Thank you very much, Matti, and thanks everyone for attending. I had a lot of fun. It was a bit of a different style. There was no live coding this time. I hope to get back to doing the occasional live coding stream at some point, maybe even on this. But yeah, tonight it was more looking at code and trying to like understand how the various pieces fit together. So thanks everyone. Thank you, Matti, and talk to you soon. Good night.